So I know you rushed right into this video because you had to know what's this super important, super famous method. And it turns out it goes by a couple of different names. I like to call it the method of the lucky guess, or just the lucky guess method. Now, you might be thinking, wait a minute, guessing? Yeah, guessing. Mathematics has advanced more because of a lucky and oftentimes educated guess than pretty much any other method I can imagine. Now, there's a fancier name for it, the book, and most people refer to it as the Undetermined Coefficients method. But it's really just being lucky and educated about your guess for things. Now, let me show you how it works. But before I do that, just remember there are 3 steps to what we're going to do here. The first step is we need to find the solution to the homogeneous part. The second step, and that means we're going to have to probably do a separation of variables problem. The second step is that we have to find, and that usually means guess, some particular solution, right? Y sub p. And that y sub p is for the entire differential equation. This is only for the homogeneous part. And then the third step is we put them together. We combine those. And we do that by adding them together. So this is the big picture, what we're going to be doing. So off to the side on this problem, we're faced with a linear differential equation. You can see it's not homogeneous because we've got our something times y plus some extra term there. So we're going to do step 1, and we're going to do step 1 to find what our y sub h is. And so for finding y sub h, that means that we're going to kind of ignore everything else except those first 2 terms, the dy dt, the derivative, and the term that has a multiple, or in this case a constant, but something times y. And we need to find the solution for that. That's our homogeneous part, right? And so if you were dealing with the equation dy dt equals negative 2y, I hope that you can see this and go, oh, wait a minute, that's just like one of those exponential, in this case, decay problems from way back in the beginning of chapter 1. If you need to, you can take the time to integrate both sides and move the y to the other side, and you would integrate 1 over y dy equals the integral of negative 2 dt. And after some work, you'd find out that y sub h, and that's what we're finding in this case, y sub h, is going to be equal to some constant c times e to the minus 2t. Now, you could go from here to there because you know this is an exponential decay differential equation. You've probably done enough of these, or if you haven't done enough of them, you will definitely do enough of them where you'll be able to see it over time. So this is finding our y sub h. So we got that part. Check. Now, the little bit trickier part, and this is where the method of the undetermined coefficient steps in. So part 2, we have to find our particular solution. And this finding the particular solution has some kind of sub-steps. So I'm going to write these sub-steps out, and I'm not going to number them or anything like that, but I'm going to write them out so I'm explaining what I'm doing here. So the first little step here is we're going to write the entire dE out, right? Okay, so nothing too scary. And our entire dE looks like this. dy dt equals negative 2y plus e to the t. Now that's the entire dE, not just the homogeneous part. Okay. Now what we're going to do is we're going to move all terms with a y in it to the same side. And I'm going to move them specifically to the left side. And so that means the e to the t stays there, but this guy's going to move to the other side. So we have dy over dt plus 2y equals e to the t. Okay, so far so good. Now this next step, this next part of finding the particular solution, says that you need to examine for what, or for which type of solution to expect. And I'll explain that here. take a look at this equation. This is saying, literally, take the derivative of a solution, add it to 2 times that solution, and what you get is e to the t. So any solution, anything that's a solution for this differential equation must be its derivative added to 2 times itself equals e to the t. What kind of a function would you expect? What type of a solution would you expect to plug in for y here and have it spit out an exponential like that? I'll give you a second to think about it. Can you imagine me putting in some kind of a polynomial, t squared plus 3t, here, and having it magically make an exponential? Hopefully you're sitting there thinking, no, that's not possible. There's no way that would work. As a matter of fact, you wouldn't expect to be able to put in a polynomial. You wouldn't expect to put in something like a sine or a cosine here and have it come out to be e to the t. As a matter of fact, there's really only one kind of function that we would expect to plug in for y here and have it come out to be e to the t. And that is an exponential. So our educated guess, and that's what we're going to call this, our educated guess. And this is why we call it a lucky guess, but it's really an educated guess in this case, is we'd expect an exponential. So what is our guess? So if I can got to find a different color here so it doesn't stand out entirely too differently. Oh, there it is. I'll do that one. So let's try a guess of something like y equals a e to the t. Now you might think, well, why is it just e to the t? Why not e to the at? The problem is that when I take the derivative of e to the t, I don't actually change the upstairs at all, right? So e to the t is its own derivative kind of thing. So I'm just going to stick a constant, and that's where that undetermined coefficient moniker comes from. A is that undetermined coefficient. So I'm just going to say where a is a constant. And I don't know what the constant is, but I know that if I were to plug this in for y here and here, that I might be able to figure it out. So I need to know now what is dy dt. And so taking the derivative of this is not too tough. It's just itself, a e to the t. No big shakes. And because I've guessed this and I know what its derivative is, I can test my guess. I can literally substitute it back in. So I'm going to, the next phase in this process is test the guess to find what a must be. In other words, there's a value for a that we can pretty much guarantee it has to be something, but we don't know what it is yet. So I'm going to throw that one in. I'm going to say, okay, so I'm going to use my differential equation. So I'm going to say d dt, the derivative with respect to t of my guess, which is a e to the t. And that's got to be equal to, I'm just plugging this right back into the original differential equation, -2 times the y, which is the guess, a e to the t, plus e to the t. So all I did was I substitute my guess, here, and now I can proceed. So the derivative of this thing I know is just a e to the t. This over here is -2a e to the t, and plus e to the t over there. And you'll probably recognize each one of these terms has the same e to the t factor, right? So I'm going to kind of move things around. I'm going to move the things with a to one side, and let's see what we get. We wind up with, if I kind of maneuver myself, 3a times e to the t on one side and e to the t on the other. Now the only way 3 times a number times e to the t is equal to e to the t is if that number right there is equal to 1/3. Another way of thinking about it is if I imagine the e to the t's are both 1, then 3a equals 1. That means a must be equal to 1/3. So what we've just done is we've found this to be the value. 1/3 is the value of the undetermined coefficient. And that undetermined coefficient, that's the lucky guess part of this, right? So what does that mean? Well, that means we're done with step 2 because we've just found out our particular solution, y sub p of t, is equal to 1/3 e to the t. Right? That was our guess right there. We know that a is 1/3. So we now have our particular solution. So let me go all the way back up here and say we now have that part done. And then the third part is really easy. All I have to do is add them together to get my full solution. So step 3 comes in, and for step 3 I say we're going to state the general solution. Oops, let me scoot that up so you can see it. And we state the general solution by saying y of t is equal to these two parts that we just found. The first one was our y sub h plus our y sub p. And all I have to do is just add them together. I didn't even need to say this, but I'm saying it because I want you to see and kind of reinforce that. So y of t, the general solution for this equation, for this differential equation, is constant times e to the negative 2t plus the particular solution that I just found, which is 1/3 e to the t. That, my friends, is the general solution for this differential equation. Now, the good news is that we can check it. We can verify it. And we can verify this one of two ways. We can sub it in and check. And we could do that, kind of using calculus, kind of take this, throw it in to my differential equation way up at the top. I can take this and then throw it in for y up here and verify that it works in the equation. The other way, of course, is to just have Maple do a desolve, right? Whoops, sorry. And the good news about Maple is it's pretty fast. The bad news about Maple is sometimes you have to kind of reinterpret what it's telling you in terms of the solution, right? Because sometimes the output doesn't look exactly like what you came up with, even though they might be the same thing. So take a second. I want you to verify this by one of these two methods, if not both, just for practice. And make sure that what we came up with here really is the general solution for the differential equation. And we'll come back in the next video for another example.